All right, today it's going to be pretty simple. We're going to explore just one thing. That one thing is going to be establishing a Voronoi pattern. Um, it's basically a complex cellular sort of subdivision. That's the simple form I'm going to give you as a definition for now. But it's a popular geometrical sequence, I think, in architecture these days, and it functions both in 2 dimensions and in 3 dimensions. So to do this process, let's quickly talk about our larger objective, right? So these forms, we wanted to emulate folding, right? And we did that successfully. We got the Grasshopper script to actually fold like it was a piece of paper. When we're going to map the pattern across it, you can map the pattern across it as is, but it's kind of a complex sequence because you have to create the pattern, then you have to map the pattern in all three orientations again. So it's basically going to be the same definition you're doing here, but with a pattern instead. And rather than kind of exhausting the same thing twice and dealing with small, tiny nuances between the two, I want us to focus on the fact that this is an assignment and we're kind of at a deadline, right? So what we need to think about as you start to understand these software packages a little bit better is, when do I make concessions from one software to the other? When do I decide it's not worth my time to, exhaustively try and figure it out in Grasshopper and just push it back out into Rhino and figure it out from there? Usually that determination happens at the detailing level. So for instance, if it's a building and you need to do like doorknobs and cables and lighting fixtures and stuff like that, that kind of detailing level is not necessarily or not usually going to be practical in Grasshopper, at least in my opinion. At least not for the way most of us use it academically. So our process here today is going to be to take these forms and flatten them in Rhino. So that way we have the surface already flattened. We can map whatever geometry onto it we want, and then we can just fold it back up into the position we want it to be in after we've cut it out on the laser cutter, right? So this is now, the actual rapid prototyping sequence. If you are concerned about designing with it mapped onto the form itself in Grasshopper, then you're going to have to go through the process of remapping the pattern into all three orientations and then subtracting it from the original surfaces. But for our purposes, we're under a deadline and we need to get a laser cut out, so we're going to look at it 2-dimensionally from this point forward. Okay, does that make sense to you guys, doing that, making that decision? So later on in the semester, we're going to be simulating that sort of decision making, but I'm kind of walking you through it here today. So to do the flattened surface, right, we're going to do a pattern and subtract it from the surface itself. There are a couple of ways of doing it, but basically if you're going to unroll it, now that these right now are individual surfaces, we have to join them together to make it a polysurface, because when I unroll it, I want to say explode equals no, so that they all go together. Okay, and that gives you the surface that you are going to work on. So with this surface, we're going to have to actually break it down using a pattern. And let me quickly show you the pattern that we're going to use. So Voronoi. So this is kind of your Voronoi pattern, right? So it emulates the cellular makeup and irregularity that you find in nature, sort of. Or at least that's how we use it as designers in most cases, or in a lot of cases. But we're going to be doing something like this. You can create three-dimensional forms with it, like you see here, or you can create two-dimensional forms with it. But for us, we're just using a simple frame for it. So we're going to create the cells and then reduce the size of the cells and then punch them out of the actual surface so we can laser cut it. Are there questions about what we're doing? It's basically going to be an unrolling of something like that. All right, so let's get started. I'm doing it just in the same definition that we set up yesterday. Wow, looking back on that, we did a lot yesterday. We really did. So I'm just going to do it in the same definition we did yesterday, but to make things easy on myself so I don't have to, do multiple surfaces or anything like that, I'm going to merge this poly surface into a singular surface, right? Because it was unrolled, so that means that it is planar now. So I can just type in merge all faces. I don't know if Jeff showed you that one yet, but if you have two planar surfaces that are coincident, you can merge all faces and it turns it back into one solid plane like this. So I'd like you to do that now with whichever iteration of your exports or bakes you find to be the most attractive. And I'll just pause till we get there and then we'll move on. So once you have the flattened and merged surface, we're going to start developing the actual pattern. So I will say this about today. We're only doing one thing, and it's a very, very simple thing, but pretty much everything we're dropping in is going to be kind of brand new. Okay, so there's going to be a lot of things that you haven't seen, a couple things you have, but just don't worry because it's not going to be overwhelming, I think, as long as you think about them in groups, I think. Anyway, I don't know. We'll see. So let's start off with the first really weird one. It's the actual Voronoi itself, and then we're going to work backwards. So if you go under, actually I don't know where it is, so let's just go with Voronoi. Voronoi is spelled V-O-R-O-N-O-I. It's weird. I don't know the origin of the word. I'll find out for you though. But we're going to put in this one that's called Voronoi groups. If you look at the descriptions, right, they all have slightly different descriptions, kind of like rotate, right? So this one says, compute a single 3D Voronoi cell, so that's in 3 dimensions. Voronoi group says, compute a custom set of nested Voronoi diagrams. This one is a volumetric Voronoi diagram for a collection of points, and a Voronoi diagram for a collection of points planar. So notice how it's creating geometry off of points, right? So it kind of gives you a little bit of a hint as to how it might work, right? So the long and short of it is that it's going to be based off of center points, which makes it kind of easy for us, I think. So anyway, we're going to drop in Voronoi groups. And what you can see is that if you read all the information that it's requesting, it's not exactly very descriptive. So that's the part of today that might not be so easy to download, but I'm going to walk you through every step of the way. It's going to ask you for the boundary, which it's showing as a domain, but really what it's going to want is a rectangle. It's kind of weird. And then it'll ask you for the points as a list. So the short version is if I have a rectangle and I reference that rectangle in, I can plug it in here. And then there's this other one that I think I showed you a little bit about before, but it's under Vector, Grid, Populate 2D. So Populate 2D right down here is trying to kind of create its own definition. But if I plug that rectangle into Populate 2D, what you'll see is that it's actually populating the rectangle, right? And I can plug that into the group, and look at that, we're already done. We've got a Voronoi, right? So very different. but also very easy, sort of. So to get us going, I think we should just get that on screen, and then we're going to start moving it into an actual adaptable surface after that point. Okay, so why don't you drop in these components. Voronoi group is under mesh triangulation. And populate 2D is under vector grid. While you're at it, you should also probably reference in the surface. So just put this one kind of off to the left here and reference your surface. Okay, so now we're kind of playing, connect the dots. Because we know where we're beginning, we know where we want to get, and then we'll connect the two.